Hi there. Did you know that there are about 100 billion stars in our Milky Way galaxy and yet we can only see around 2,500 of them with our naked eye? Crazy, right? In this video, we'll figure out how astronomers learn about stars. Let's begin. So what exactly are stars? Well, they are massive celestial bodies made up of hot gases, primarily hydrogen and helium. A star fuses hydrogen into helium in its core. The energy thus produced is emitted mostly in the form of heat and light, while a fraction of it is used to balance the inward force of gravity. The total energy emitted by a star per unit time is called its luminosity. But since this energy is emitted in all directions and some of it is lost on the way, we only receive a small fraction of it when observing. This energy received by an observer per unit area per unit time is called a star's flux. But the brightness of a star depends upon its luminosity as well as its distance from the observer using the inverse square law that we have already described in an earlier video. This equation is very basic but rather interesting because notice that on the left-hand side is flux, a quantity that astronomers can measure. While on the right-hand side there are two unknowns, the distance to the star and its luminosity. So, we need techniques to determine at least one of these indirectly in order to estimate the other. We have already described several methods of distance measurement in an earlier video. Do check it out if you haven't already. Recall that magnitude is a dimensionless quantity used to quantify the flux or luminosity of an astronomical object. Since the human eye's response to light is logarithmic, magnitudes are measured on a logarithmic scale. In the currently used system, magnitudes usually defined for a given waveband are such that magnitude 1 star is exactly 100 times brighter than a magnitude 6 star. That is, each step of magnitude corresponds to an increment in brightness by a factor of fifth root of 100, which is approximately 2.51 as shown here. The magnitude measured directly from the flux obtained from an object is called its apparent magnitude, represented by the letter small m. Using the inverse square law, astronomers assign an absolute magnitude capital M to every star as well. This is defined as the apparent magnitude of a star if it were located at a distance of 10 parsec from us. You must have looked at the Orion constellation in winters and noticed the different color of Betelgeuse and Rigel, the opposite stars in the constellation. The difference in their colors betray the difference in their average surface temperatures. While Betelgeuse has a surface temperature of around 3900 Kelvin, it is much cooler than Rigel, which averages around 13,000 Kelvin on its surface. The relation between color and temperature exists because all objects above a temperature of absolute zero emit radiation at all wavelengths, although with varying efficiency. An ideal emitter is the one which is capable of absorbing all energy incident on it and re-radiates it with a characteristic spectrum. Since this emitter reflects no light, it is called a black body, and the radiation it emits is known as the black body radiation. Roughly speaking, stars and planets are black bodies. Even though a black body radiates energy at all wavelengths, its spectrum peaks at a particular temperature T corresponding to a particular wavelength lambda max. The relation between these two is given by the Wien's law. This implies that by finding the wavelength at which the spectrum of a star peaks, astronomers can find its black body temperature, that is, the temperature of its surface, assuming that the star is a perfect black body. The blackbody spectrum shows that as the temperature increases, the blackbody emits more energy at all wavelengths. At the turn of the 19th century, two physicists independently derived that the luminosity of a blackbody with area A and temperature T is given by this relation. Therefore, if we assume the star to be spherical, the luminosity will be given by the relation luminosity is equal to 4 pi r squared sigma T to the power 4, where sigma is known as the Stefan-Boltzmann constant. Since stars are not perfect black bodies, the temperature obtained using this relation is called the effective temperature of the star. This also implies that more luminous stars are bluer and hotter, while the cooler stars are relatively less bright and optically red. Several decades later, German physicist Max Planck theoretically derived the blackbody radiation curves using the fundamental principles of physics. We now know this relation between wavelength and the power of blackbody at any given wavelength as the Planck function, where the constant h is known as the Planck's constant. The magnitude estimated using energy in all wavebands is called the bolometric magnitude. But we hardly ever measure the energy emitted by a star at all wavelengths. Usually, we are limited by specific instruments and technology, for instance, using filters for observations. A filter is a device which allows photons only in a certain wavelength band to pass through. As a consequence, the energy emitted by a star in a given filter can be converted to its apparent magnitude and, with the knowledge of distance, to absolute magnitude. Traditionally, a star's magnitude was often measured using the UBV filters, where U stands for ultraviolet. This is a filter centered around 3650 angstrom. The B stands for blue, centered around 4440 angstroms, and V is for visual at 5500 angstroms respectively. The difference in magnitudes of two distinct filters is called the color index of the star. Remember that smaller stellar magnitudes correspond to brighter stars. Therefore, a star with smaller B minus V is bluer than a star with larger B minus V, and so on. The difference between the bolometric and visual magnitude of a star is called the bolometric correction. Besides their brightness, position, motion, and distance, astronomers also devised methods to determine the internal structure and chemistry of stars. When scientists such as Newton passed sunlight through a prism, they discovered that it splits into a rainbow-like spectrum superimposed by a number of dark lines on it. By the year 1814, the German optician Fraunhofer had catalogued 475 of these dark lines in the solar spectrum, which are now called the Fraunhofer lines. A decade or so later, Bunsen and Kirchoff conducted various experiments to understand the spectral lines, which led them to three laws summarizing the production of lines in a spectrum. These are now known as the Kirchoff's laws. These laws state that a hot dense gas or hot solid produces a continuous spectrum. A cool diffuse gas in front of a source of continuous spectrum produces dark spectral lines called absorption lines in the continuous spectrum. A hot diffuse gas produces bright spectral lines, also called emission lines. These results further led to the knowledge that stars like our Sun are also made up of many elements found on Earth. You would be amazed to know that the element helium was identified in the solar spectrum almost 3 decades before it was discovered on Earth. The spectral lines could also be used to measure the Doppler shift, because for individual stars, the radial velocity is much less than the velocity of stars. A star spends most of its lifetime in a narrow region on the luminosity temperature plane. This is called the main sequence. For a main sequence star, the luminosity is found to be related to mass as shown here. But this is an approximation. In reality, the relation between luminosity and mass changes according to the luminosity of the star. These relations in turn imply that the lifetime of a star on the main sequence depends upon the ratio of its mass to luminosity. While hot, massive stars are short-lived, smaller, cooler stars live for a very long time. For comparison, consider that the lifetime of Sun is around 10 billion years, but a star 10 times as massive as the Sun will be around for only 10 million years. On the other hand, a star with mass a tenth of the Sun will be around for almost 13 billion years, that is the age of the universe. So far, we have learned that the knowledge of blackbody radiation allows us to measure the luminosity, effective temperature, and composition of stars. An estimate of mass can be obtained from its luminosity, but the only direct way to measure the mass of a star is to study the gravitational interaction of the star with its neighbors. As we have discussed in an earlier video, the Kepler's laws allow astronomers to measure the mass of planets in our solar system. But since the gravitational force is universal, it is amazing that the same laws can be applied to other stars orbiting one another as long as all orbits are considered around the center of mass of the system. Thankfully, nature provides many such opportunities because at least half of all the stars are found in multiple star systems of two or more stars orbiting around a common center of mass. For instance, by considering the centripetal force to be equal to the gravitational force, the Kepler's third law can be derived as shown here. This relation shows that the total mass of the system can be determined if we know the orbital period and the radius vector, that is, the separation between the two stars. The Doppler shift in the spectral lines can be used to get the velocity v and hence the orbital period of the system. Binaries can actually be classified into different categories. The simplest of these is the visual binary system. As the name suggests, both stars in this system can be resolved and observed independently. If the orbital period is not too long, it can also be monitored for both of them and their angular separation from the center of mass can be determined. If the distance to the binary is known, the linear separation between the stars can also be determined. An example of a long period binary is shown here. Note that the stars are gravitationally bound. If two stars are just located next to one another in projection but actually distant from each other, that is, not interacting gravitationally, they are called optical doubles. When the orbital plane of a binary system is oriented along the line of sight of observer, one star seems to pass in front of the other, causing a change in its luminosity. If such a star is continuously monitored, the periodicity in the change in luminosity are detected. These light curves can then be used to estimate the luminosity, effective temperature, and radius of stars. But most binary systems are either too far away to be resolved as visual binaries or the component stars are too close together to be resolved separately. In fact, majority of binary systems have been detected by Doppler shifts in their spectral lines. Such systems are called spectroscopic binaries. If a binary system is unresolved into its components, then the spectrum obtained from it will actually be a combination of the spectra from each of the component stars. As these stars orbit each other, one star, say A, may be moving towards us while the other B may be moving away. The spectrum from A will therefore be blue shifted to shorter wavelengths while B's spectrum will be red shifted. If the stars are moving across our line of sight, then no Doppler shift occurs, so the lines stay in their mean positions. As the stars continue orbiting, A will recede, so its spectral lines will move towards the red end of the spectrum and B's will move towards the blue. This is shown here schematically. Now, if the orbital plane of the binary is exactly along the line of sight of the observer, the ratio of masses of the component stars is given by the inverse of ratio of their velocities. More specifically, their radial velocities, which is what we actually measure using the Doppler shifted lines in the spectra. When the two spectral lines can be resolved in the spectrum, the system is known as a double line binary. For a system whose orbital plane is along the line of sight of the observer and the orbits are perfectly circular, the radial velocity curves are perfectly sinusoidal. However, if the orbital plane is inclined to the line of sight, the amplitude of the curves is somewhat modified. But in most cases, the orbits are elliptical rather than circular, and this changes the shape of the sinusoidal curves as shown here. In other words, the degree of skewness of the radial velocity curves increases with increasing eccentricity of the orbits. Assuming that the angle of inclination of the orbital plane is I, the relation between mass and radial velocity is modified as this because the observed radial velocity cannot exceed total velocity times sine of I. As a special case, note that if the direction of motion of stars is normal to the line of sight, the observed radial velocity will be 0. Consider a special case of an eclipsing spectroscopic binary where the small star is completely eclipsed. In such a situation, by carefully tracking the period of eclipse, time of first contact, and the minima in the radial velocity curve, the radius of the smaller star can be determined, assuming the orbital plane to be normal to the line of sight, given that the semi-major axis of the orbit of the smaller star must be larger than the radius of both the stars. In this example, let's assume that the smaller star is hotter than the larger one. Hotter is the smaller star, deeper will be the dip in the light curve at the primary minima. From our discussion in the beginning of this video, we know that the flux is proportional to the fourth power of the effective temperature. This implies that when both the stars are visible, the observed flux is given by this expression, where the subscripts S and L represent small and large star respectively. K is a constant which depends upon the detector, distance of the system, and material intervening between the system and the observer. Now, when the smaller, hotter star is fully eclipsed at the primary minimum, the observed flux is given by this expression because only the larger star is visible. But then at the secondary minimum, the smaller star will obscure part of the larger star and the observed flux will be given by this changed expression. Since K cannot be determined exactly, the ratio of stellar temperatures can be determined in terms of the observed flux of the two stars. To summarize, different categories of binaries help astronomers determine different parameters of stars, some of which we discussed in this video. We'll continue learning more about stars in the next video. Let me know what's your favorite fact about stars, or is there any other specific topic you want to dive into? Leave your thoughts in the comments below and don't forget to hit that subscribe button for more cosmic adventures. I'll see you next week. Until then, take care.